Okay, welcome to our Bucky weekend call, December 6th and December 7th. We're doing a fuller explanation, and um, thought I had it loaded here a minute ago, and I was going to tell you what page we're on, but it's the part after might, and I think it's couple. So we'll examine that as we go. Um, and we're going to go ahead and get started. Richard, how are you feeling today, and what do you anticipate getting from today's call?
Mm. Well, I was saying earlier when we're off record, uh, good and not so good. Uh, a good a good time this morning on the trim tab group. We were going to talk about time as a dimension or not, um, and Lionel, who was going to lead us, wasn't able to come on. So we did what was considered a free flow. We could just talk whatever we wanted, and it was really amazing. We had colleague in Texas and uh, and several other places in the East Coast, and myself in Canada, and one in Colorado, and it and one from California. It was all kind of free flow, but they all seemed to interconnect with each other, and talking about the complexity of invisible relationships. Um And one fellow has been working on the idea of a better AI system that could actually kind of work with feelings. And so we got into a really interesting discussion using Fuller's formula, R equals n squared minus n over 2. And, and we really started thinking about some practical applications of that formula. Um, so yeah, and then as I say later this afternoon, my wife's run into a problem of a knee joint that seems to have given out on her, and so now we're using a makeshift sort of office chair on wheels to kind of move around in the house. Um, so I may get a call to say come out here or do something, but otherwise I'm I'm free to be involved and looking forward to getting even a deeper understanding of might. And I think expanding on, I did what uh, Fred was talking about in terms of taking a model or a diagram and just stare at it and sort of focus in. And and I think it really helped me understand how you get from a symmetrical sort of modeling down to an asymmetrical. Um, and
Yes.
so thank you, Fred, for that encouragement to just visualize what you're trying to work your way through, and I think it does help. Uh, so so over to you, Fred, and thinking of you on the 6th, which is now the 7th, and hope that all went the way you were thinking about it, and the kind of anxiety that you had was not not what you expected, and everything went well. So how are you feeling, and what's your takeaway? Or
Thank
not
you,
takeaway,
thank,
but what are you expecting to do today?
thank you, Richard. I'm sorry to hear about your wife. I hope it's nothing that gave out, just a little bit of fatigue, and that tomorrow morning, with a little bit of rubbing and
Yeah.
goodwill, she will be fine. I really hope that, because when somebody starts to have difficulties moving around, it's really a burden for her and for you, and it's not a good feeling. Um, I'm feeling pretty good today. I woke up and I was at peace. I was rested. I was at peace, and I was like a page had turned. It's a little bit of a overbeaten allegory, but really that was a feeling this morning, and that was a feeling that I anticipated last night. Last night I was exhausted after a very long day. It was a public day, which is there were 24 families that were together in two buses, each with 3 to 4 members, 3 to 5 members going together. And as in most Chinese public settings, there's a cultural inadequation between my expectations and what they're offering. They're noisy. They like noisy. Their celebrations are noisy. They are bright in colors. They are a little bit intrusive. There's no real ability to be with yourself, with your own thoughts. It's to me, it's a little bit more like a performance and hanging in there in order to go through it. But anyway, that's their culture and that their country and that's how they do things. So that was fine with me. So we went there. Plus, I had to spend the day, as I usually do when it's something like this, and there's a uncertainty about what amenities or facilities there will be down the road. I spent the day in dehydration in order to avoid needing trying to find a tree in the middle of the ocean to release myself. And so I came back home. I was exhausted. I had a headache due to the dehydration. I ate something. I tried to go to bed and I could not sleep. So I hydrated myself, and then I kept waking up all night to go to bed to go to the loo. And but anyway, Lucy just was sent away, and her friends were there. They were very supportive, and everything went very well aside what I just mentioned, which is just a cultural inadequation. Uh, that's it. So, but this morning is like I said, a page has turned, and I'm ready to move on. And it was my best outcome, the best outcome I wished for. So that's where I am at now, and that's very good. So my expectations today were interestingly, I have no expectation. I not that I expect nothing will happen, but I don't have any specifics. So that's I'm open to whatever comes my way. So thank you very much for your support, and I know you keep Lucy in your thoughts, and me myself also in your thoughts at the approximate time, and that was also a thought that kept me up uplifted. Is that the correct word? Uplifted. So, and I'm sure Lucy felt it also. There we go. So, Lee, how are you feeling today, and what is your desired takeaway? You muted.
I'm feeling quite good. I am still in a dark hole with mites running around. I haven't yet figured them out yet. So hopefully today it will expand on my idea of what a mite is. And because I can't hear anybody, it's not working. But I'm hoping and praying that I can read his screen from way over here and get what is supposed to be said and learn more about these little mice. Steve, how are you feeling and what are you wanting to take away?
Well,
I'm a little frustrated because I've been coping with this computer for the last 45 minutes, doing what I can to get screen showing and things showing, and I'm not able to do it, Lee. So I got the TV going to show my screen a while ago, but I couldn't control what content was going on it. And um, so life is happening. Um, I'm excited about I admit I'm knee deep in what's going on here with our studies both on Wednesday and or maybe I'm up to my nose um, between our studies. And I think I kind of got a little bit about the mites, maybe. Um, just I understand that I don't understand them, and I think I understand why I don't understand them. That's cool. And tonight we're on page 224. We're going to start with coupler. And I did a I'm kind of anticipating that Manu is going to be here, and he was going to talk a little bit about. He seemed quite convinced about mites and the role they would play, and he seemed to say things that were absolutely against what was quoted in fuller explanation from synergetics. And then, Fred, you brought up the not Schrodinger, Schoenhardt, the Schoenhardt polygon. Here comes Lee. Wow, Lee, you dropped out. The Schoenhardt polyhedron, and but it was that. But as we did the research, it was came out in 1928, so that was before Bucky. And what I pointed out, and maybe Manu will be joining us, but I remember that Manu, when I was doing real estate consulting, a lot of times I wouldn't remember all the little details. I just had a real sensibility about solving a problem. And then later, as it went down the line, the details would appear to themselves. And usually I was right, even though most people didn't agree with me. So I'm really looking forward to Manu manifesting his awareness because I really trust his. He has the most topological brain I know of, and I'm delighted when he shares. And yet it's frustrating to me when Bucky's being quoted and something else may be true. So we'll just see. Let's hope Manu shows up and we're going to continue. We're on page 224, and I'm going to bring it up here if I can get my, wow, I don't have a cursor. Oh, there it is. Okay, good. I'm going to share my screen. I really don't like how Zoom changes its options on the control panel based on what's showing. And that frustrates me a little bit. Okay, here we go.
Steve,
Yeah,
may I have your magnifying glass?
yes.
Thank you.
You're welcome. Okay, good. And our screen is showing. So I'll read a paragraph or two here to get us rolling, and then hopefully somebody else will want to read as we get going. But here we go with coupler. Fuller's coupler is an irregular octahedron made of 8 mites. Oh my gosh, here more mites going on. We've got 8 mites going on. This looks like a mite to me right here. That thing. There's 2 mirror mites at 90 degrees, and then there's a weird mite. So this is the AAB, right? If I remember right from last week. And we're saying the or 16 A modules and 8 B modules. See figure 13.7. Each mite is 1 octant of the coupler. So that I think an octant is an eighth. So each mite is an eighth of the coupler.
What it
1,
means is
2,
that
3, 4, 5,
8
6.
mites is what it means is that 8 mites is equivalent to 16A and 8B.
Right on. In fact, there's your A and A.
Because a mite is composed, one mite is composed of 2 A's and 1 B.
two A's and one B, and there it is right there. And it looks like that
Yes, correct.
this part of the octahedron is one mite. So if we went one there, then one behind there, then one here and one here, there's four on top and four on the bottom, so that makes eight. Given this composition, the semi-symmetrical coupler is clearly a space filler. I don't, not so clearly, but there you go. Because of the mite's newfound mirror symmetry, the coupler does not have to have equal numbers of positive and negative B modules. Any eight mites will make a coupler. The special octahedron has two equal length axes, which will be referred to as X and Y. As I look at the diagram here to get situated with X and Y. And a third shorter axis, Z. Well, I'm not seeing that at all. This point of intersection of the three axes will be called K. So, okay. Okay, if Z is going all the way vertically down through the octahedron, and X and Y,
It's that you're trying to look at XY, which is an edge. Don't look at XY. Look at XK and the link to
right,
to the
and
opposite
KY,
vertex,
yeah,
and YK and the link to the opposite vertex. We're looking at, you don't want to look at edges, you want to look at axes of symmetry.
right. Thank you. And the point of intersection will be the K. The X and Y axes outline a square equatorial cross section, which we can now identify as the face of a cube.
Where?
That's that square thing right there. If you think of the cube octahedron,
Oh.
I don't know. Face of a cube. In fact, the coupler is two 1/16th cube pyramids back to back.
Can you see it?
Well, that's 1/16th right there because there's one,
The
two,
other one.
three, four.
Look at the other one. You've
Look
got
at
the
this one over here.
x-axis, you've got the x-axis, you've got the
Yeah,
z-axis, and the
yeah,
y-axis all going
yeah.
through K. Now, if you take x and the n of x, y and the n of y, then those four vertices form a square.
Top and bottom.
If you go
The
all the
f-
way from x to k to the opposite vertex, and from y to k to the opposite vertex, then you have x, y, the opposite of x, the opposite of y. This forms a square.
okay, so it's just out here in space.
Yes.
Okay.
Okay. Now, when you take the plane defined by those 4 points, the square, it's a shared square between two four faces pyramids that are opposite to each other. And the top of the apex of the pyramid is the endpoints of the z-axis.
Okay. I'm
Okay.
seeing part of that.
Okay.
So I feel good about seeing part of it. How about you, Lee?
I'm seeing it.
Oh, well, good. The other cross sections, XZ and YZ, are diamonds. XZ and YZ are diamonds, the other cross sections. In fact, the exact shape of a rhombic dodecahedron's face. At this point, we shall not be surprised to learn that the splitting the coupler in half along the either diamond cross section isolates 1/12 of the rhombic dodecahedron, since six 1/2 couplers make a cube. 12 1/2 couplers split the other way make a rhombic dodecahedron. Well, okay. Aptly named the new octahedron joins both pairs of cubes and pairs of rhombic dodecahedra. Fuller's nomenclature proves quite logical. We give it the name the coupler because it always occurs between the adjacently matching diamond faces of all the symmetrical, all space-filling rhombic dodecahedra, the spherics. The coupler's different pairs of opposite vertices reach to the geometric centers of two adjacent polyhedra, cube or spheric, depending on the orientation. Incorporating their shared face, as a cross section, figure 13.8a and figure 13.8b. Half of a coupler belongs to one cube or spheric, and the other half to its neighbor. So the coupler literally couples, well, not everything, but a couple of space fillers. Okay, well, it makes sense to me, although I couldn't tell you what I just read. Here's your dodecahedron up here, though. Here's a dodecahedron down here, and here's the octahedron inside there. I can see that clearly. Here's the octahedron inside here, and here, as Fred, you explained, we extend these axes up and we can visualize a cube. A cube from, yeah,
Top
I
and
was able to
bottom,
do
yeah.
because of your, I said they extend out into space here, and you agreed, and that's exactly what that picture's showing. Any other comments or questions or feedback? Maybe it's pretty obvious, two dodecahedra and an octahedron joining them.
Can you show me the diamond?
The diamond, an octahedron is a diamond.
Yeah,
Oh,
and
If
that
you
shows
look-
up nicely in that diagram.
If you
Yeah.
look at 13.8 coupler, the B diagram, there's in between those two shapes, there's there's a octahedron,
Right.
and that octahedron is no, I'm confused here. It's not that. I can't see in 3D. Sorry, it's too complicated.
I
that
hear
way.
you. I hear you. But we both
Uh,
see, Lee, you see the octahedron here, and you see the
Yes, I
octahedron
do.
over here, right? These are diamonds. But also, Fred, I'm going to point out that when Bucky describes the dodecahedron, he calls these two-dimensional diamonds. He calls these
Yeah.
diamonds as well
yeah,
here.
yeah, yeah. There's more like a rhombus than a diamond.
Right.
Right.
And in fact, he calls them, at some point, they become hinged diamonds.
Okay, if you go to A, you can all see the square now between those
Yes.
two cubes. Okay.
Uh-huh.
Now there's the diamond is the square is flat like this. If you can see my hand and
Mhm.
it's small,
Yeah.
and the diamond is a plane that goes through the apex of the pyramids and two of the and the Y and the end of Y plane. That's one of the diamond.
Okay.
The other one is the one that would go like this.
Yeah.
And these are 2D structures, so they're rhombus, rhombi,
Right.
to use a Latin plural.
So that's a 2D diamond there, Lee.
Yes.
Okay.
And the dodecahedron is, if you look at the faces, all these faces are diamond shaped. They're two-dimensional diamonds.
Yeah.
Yeah, they're not squares. They're kind of squished, so they become like
Yeah.
a diamond. Cool.
You also get at least I get in B, you want a hexagonal cube.
Yeah.
Oh, yeah. I see that.
Actually, I have a magnet structure in the other room that shows the hexagons very clearly. That are created by a bunch of these octahedras stuck together in the um, matrix, in the isotropic vector matrix. Cool. I can go get that maybe if it'd be helpful. The respective unit radius backspheres. So Fuller continues, the coupler's role is cosmically relevant for rhombic dodecahedron are the unique cosmic domains of their respectively embraced unit radius closest packed spheres. That sounds just like Bucky. The coupler therefore connects the centers of gravity of adjacent spheres, and its and its domain includes both the spheres and the intervening dead air space. This observation explains why the coupler's volumetric center was labeled K, and it makes the exact kissing point between tangent spheres in a close packed array. This is the K thing up here. There's that K. Okay. We're going to the next page, 226. Does anybody else want to read? I don't mind reading further. I'm not too distracting. Okay, go ahead.
I can read it, but you need to tell me if my English is legible.
Okay, good.
Would you like me to do that?
Yeah, please go for it. It's good
Okay.
practice for you and for me.
Okay. So 226, top of it.
Right.
Now we have the complete story behind Fuller's somewhat dense explanation of his coupler. And here is quote synergetics. The uniquely asymmetrical octahedra serve most economically to join or couple the centers of volume of each of the 12 unit radius spheres tangentially closest packed around every closest packed sphere in universe, with the center of volume of that omnisymmetrical ergo nuclear sphere.
Yeah.
I have a prop if you want to see it. I can show you the closed packed.
Okay. It wouldn't hurt to review the close packed spheres. What, Lee?
How do you say that word?
Which word? Omnisymmetrical.
And where is the omnisymmetrical?
Right there. Can you see it?
No, I meant on the diagram.
Oh, in the diagram? Omnisymmetrical means symmetrical everywhere.
Oh,
So all of the diagram, all of these things are symmetrical. However, they are symmetrical because of the uniquely asymmetrical octahedra. So this is actually bothering me, Fred. Maybe when you show me your prop, we can get there. But everything's been totally symmetrical. It's an isotropic vector matrix. All the radials are the same size. Suddenly we have these mites, and they are asymmetrical. They are not symmetrical, but somehow they are the center of the volume of the omnisymmetrical sphere. So, if you can help me with that language, that would be cool. Okay, now does everybody know how to pin? You can pin
Can you
Fred,
see
so
my
he's everything you see. Yeah.
I can see Fred.
Okay, good.
This here is a tetrahedron,
Tetrahedron.
closed sphere packing. And if you take the point of tangency, the point where the spheres touch each other, this creates these four points form a tetrahedron, as do the centers of the spheres.
Right.
Okay?
You got that,
This
Lee?
is a this is a 6 spheres close packing.
That's an octahedron.
Yes. A regular octahedron, since the spheres have the same dimensions.
Same radius.
And this is a 12 sphere packing around another sphere.
Okay, so that's the dodecahedron?
That's the structure we just, Bucky
Yeah.
just talked about in 954-48. That's what he describes. The uniquely asymmetrical octahedra serve most economically to join or couple the centers of volume of each of the 12-unit radius spheres tangentially closest packed around every closest packed sphere in universe,
Okay,
with
lower
a
it a little
center
bit.
of volume of that omnisymmetrical nuclear sphere.
Right
So
on.
we have 12 spheres packed, closely packed around a central sphere.
Right. And that would be a dodecahedron, right? Dodeca
That
means 12, right?
would be a dodecahedron. Yes, correct.
Yeah. Okay, cool.
Correct.
Welcome, Manu. How you feeling, Manu? What do you anticipate for today?
I just hope to be on the train. I was sleeping and
Aha.
I really need sleep at this end of year. So sorry for that. That's
Okay.
cool. I see Fred already demonstrating things there. That's good.
Yeah. We have, I think, there we go. Fred's returning his screen back to a deal, and we're going to go back to reading. Do you have anything else you want to share before we begin, Manu?
The might
Do you
in the
have,
construction.
have you done
Yeah,
some
here it
work
is.
on, have you done some
Oh
work on
yeah.
the mite? You want to share
Oh
that?
yeah, I did. I did the model. Here it is.
All right. Let's hear it if you did some work on it. I mentioned that you might have work on it.
No, I did. I did effectively.
Okay.
So to start with, the definition, the might, my use of might was not appropriate.
Okay.
But the design of the stuff is here because the might effectively is a tetrahedron with a right angle at the bottom of it. But let me start this. I want, because, does everybody agree that I interrupt?
When? Right
Sure,
now? You have the
we've been,
floor
wait,
right now, Manu.
we've been waiting for that.
That's right.
Okay. All right.
I want to learn about mites.
Yes. Let me start with something. We have a tetrahedron. We have an octahedron. Everybody knows the octahedron.
Right now, what you're building is off camera, but that's okay.
Yes.
Take your time.
Yes. No, it's just going to be quite easy. I sent Joe some pictures. I have pictures, but I want to demonstrate it here. I think it's better.
Well, Joe didn't forward them to me, so
No. We didn't. I wanted it. You see, this is half a tetrahedron, octahedron.
right.
This is a pyramid. Yeah, on my
Right.
hand. You see that?
We got that. We got that.
Okay.
Which is exactly what we've been talking about in the first page.
Right.
Okay. This is a square and 4 triangles.
Mm.
Okay. Now I'm going to brace it. You see, I take this blue and I brace it here. You see what it does? So I've divided it into 2. So this was half an octahedron.
Mm-hmm.
I divided into 2 this way. Each of these is now 1/4 of an octahedron. We agree to that, huh? I've just braced it. It's, and when you brace, it does this, like wings.
Mm-hmm.
It goes in. Now, I did that with paper, and that's what the result here. I will divide it again twice. So we say this is, each side here is 1/4 of an octahedron. You can already see that it's 2 tetrahedra because all of these are equilateral triangles.
Right.
So this is 2 octahedra. 2 octahedra is 1/4. 2 tetrahedra is 1/4 octahedron. Now, I want to divide it now according. You see, one, you see, I'm just going to show it with this green. One, see this vertex that I've shown here.
Okay.
One, the second vertex diagonally opposite to it. Two, and the third vertex, this one here. Three.
Mm.
So I want to join that as a plan, as a plane. So this is one great circle. I can use the word great circle. But when I do that, I have this. Do you see that? Where I've written 1/8 octahedra?
Yes.
You see? So it divides this thing into two. And the resulting is 1/8 octahedra. Octahedron.
Yeah.
Do you see that? I've written
Yeah.
it.
And we actually have a diagram of that on our
Okay.
in the book. So life is good.
Okay.
Keep going.
All right. The second division that I did, so I already have 1/8 octahedron. The second division that I do it according to the other plane of, let me show you this, of now I first did on the plane of this one, that one, and that one. Now I divide it according to the plane that is perpendicular to that one. That is this one, that one, and this one, the short one.
Mhm.
So when I divide that into two, I have this other division here. And the resultant of that, which I've marked here, 1/4 tetrahedron, you notice that I've divided the tetrahedron into two. You see, that tetrahedron divided into two. This 1/4 tetrahedron
Raise it
is,
up.
is a mite.
Where?
And what you have seen, I've read here. You see this diagonally opposite, centered across the center of this thing, tetrahedron. What I've read,
What
A
is the
module.
mite?
Yeah, do you see A module?
Yes.
I'm turning 100 or 90, 180 degrees. Do you see another A module?
Yeah.
Uh-huh.
These two are symmetrical, back to back. They are symmetrical. So this is the left leaning and right leaning A module here. Not the left leaning and right leaning. This is what, yes, the left leaning and right leaning. Okay, you can call it whatever. He calls it the universal constant, because you see that this one and that one are of different sign. Huh? This
Okay.
one, this is you see this quarter tetrahedron here. This one, this let me just show you. You see this quarter tetrahedron here.
Right.
This and this quarter, this tetrahedron here. These two, one that I'm showing here,
Yeah.
and two that I'm showing here, they are symmetrical, like on the bow tie.
Okay.
You see that?
Okay.
So that is the universal constant. Now you are left with one A module, how will I call it? B module here, which is the symmetrical according to a face of the 1/8 octahedron. Do you see it there? I wrote it in blue, B module.
Yeah. We see B module.
Yes. So that is the model that exists. And this model fill all space. Because if you
Where's
take
the
this,
mite?
the mite is any of these right angle tetrahedra is a mite. There are 4 mites here.
Oh.
So you see, there are 4 mites, but 3 active at every time. You see the first mite here, where I write 1/4 tetra. You see that?
Yes.
Do you see the 2 mites that form 1/8 octahedron?
Yes.
And then there's one empty one here. This one allow the wiggle of this thing into filling space. In other words, like when you are mounting bricks, when you are building a wall, if you know the way people build walls, they put horizontal, especially at the corner. You put a brick like that, you build a corner, and you do another one that is going to come and fit here.
Perpendicular.
Yes.
When you're
It's going to
building
come
a
and
wall.
fit here, yes, to make the round and fill the whole space. You see that? And you repeat the same thing. What I mean is that whatever one that you take, that you pick, alternatively, you have this one or that one, this one or that one. It changes like that.
Oh,
Oh yeah, this one is empty now. Next is that when it turns, is that one that's going to be empty.
Okay.
And this fills the whole space. But you realize that the total volume of this is sub-tetrahedron. Because the total volume of this is 3/4 of the tetrahedron.
3/4?
Yeah. This is total here. This octahedron is made of this one tetrahedron, two tetrahedra here, 1, 2. But it's only 3 that are filled. It's only 3 that are filled. Look at that. This one here is empty. This guy here.
Oh,
Yes, this one where I put in my finger is empty.
Right.
And then you could do that by calculus. When you say that you have 1/8 octahedron and 1/4 tetrahedra that share an equilateral face. She says it in the construction if you read the book. This is the equilateral face that they share. Yeah. This guy, and that guy, and this guy here share this equilateral face. This face. Yes, they share this face. So if you add 1/8 octahedron plus 1/4 tetrahedron, you find 3/4 tetrahedron. Remember that an octahedron, one octahedron is 4 tetrahedra. You remember that? One octahedron is 4 tetrahedra. From the scalar relationship that we have in dividing the original tetrahedron, when we cut, we have 4 tetrahedra and 1 implied octahedron. So if I cut midway and I obtain 4 tetrahedra, and what is implied is called octahedron, it means that that octahedron is 4 times the tetrahedra. It's 4 tetrahedra. So when I take 1/8 octahedron is 1/8 of 8 tetrahedra. So 1/8 of 8 is 1. When I take 1/4 tetrahedron is 1/4. When you add 1/2 plus 1/4, you obtain 3/4. And 3/4 is 0.75. So it is sub the tetrahedron in terms of absolute volume. But the flexibility of it allows it to fill all space. And the key was this guy. The key was, again, our square. Because our square is the rhombus. If we brace our sphere, if we brace it here, then we have something else. It's mutant, and this is the way chemical bonding does. This is the bonding. And you realize now why Bucky was so about so much about bonding and the geometry. So that's it. Everybody can do this. Easy. I had to, what I did, I went to buy press stick. Here. That's press stick. And I bought A3 of this paper. And with my scissors and the press stick, I just cut. Because I had it in mind, I just cut. So it can allow you, and you see, I use this nice advertisement. I went to my wife, one of her magazines, and I stole this. I don't even know. It's an old magazine. I don't know if you.
Your wife is beautiful.
When she discovers it, what she's gonna do of me. Because there was a beautiful face. Yeah.
Your wife is beautiful. I'm not sure she's going to like you cut her picture.
No, it's not a picture. It's a picture in a magazine. I cut it because it was advertising this ladies' makeup facial stuff. I cut it out and I use it to color this one, to color the face that is going to be shared. But this is, to me, I liked it. I shared it with Joe. Joe is here now.
Yeah, Joe made it.
Yes, I have pictures of it. I have pictures of steps. So I could send you. I wanted some criticism before, but Joe seemed to, when I exchanged with him, he seemed to agree with me. So that plucked me. He gave me courage to share this here. Right. But it is quite nice. And it's always, I will never enough advertise the beauty of a pair of scissors, paper, and some scotch tape, or some press stick, or some glue. It allowed me to do a lot of things here that have demystified the difficulty of understanding what Bucky says. So I'm through, Steve.
Good.
Yes. And I think everybody can do this. And by the way, the mite is our 3D representation from inside. You remember, from inside, in 3 perpendicular directions, we imagine a cube to fill the whole space. You remember that? The Euclidean view, the orthogonal like this, 3 orthogonals, is from the mite. It's from not the mite, but the construct of a mite. From inside, we couldn't see outside. We imagine 3 orthogonal, that is perpendicular relationship, that describe our space into a catenation of cubes, where you have the hypercube. It's a catenation of cube that fills our container. We have a container. We were in a sphere, we thought that we were in a container. And then we make cubes to fill that container.
Cool.
Okay.
So I have an observation from what you shared. I'd like to share that, but does anybody else have any questions or observations about what Manu just shared? Okay, nobody jumped in, so I'm going to say this. So Lee, okay, go ahead, Fred.
I would like to thank Manu for not only staring at it as Richard
Suggested.
learned to do this week and got a lot out of it, but he went hands-on. And that's the second step after staring at it is to go hands-on. So
Good.
Thank you for that.
Kid, I wanted to point out.
That's what I wanted to say.
That's very good, Fred. Thank you very much. He went the extra mile. He stared at it and then he went and started cutting up his wife's paper. And so he got in deep doo-doo just for us. So thank you very much.
Thank you.
But Lee, I wanted to show you this because some of this I'm basically understanding. At one point, Manu stated that a octahedron, that yellow thing inside there, is a truncated, he didn't use that word, it's a truncated tetrahedron. If you take this top off here, you take this
That
top
just
off here, this top off here, and this top off here, you've taken off four tops. Those are four tetrahedra. You remove those, and when you're done, you have an octahedron in the middle.
Yes.
So there's four tetrahedron. They're the blue ones or the purple ones, and then the yellow octahedron in the middle. So I understood that much of what Manu said, and I'm happy to share that.
Yes, but where are the mites on that?
The mites are where Manu showed you. I'm not going there. I'm not going there.
You know, if you understand our orthogonal, you know, just take X, Y, Z, right?
Yeah.
No, sorry, let me take again away the Y, the right. If you take X, Y, Z axis,
Yeah.
and you take any plane that is inclined like this, that is what Becky has been drawing, you know, like in 15 degrees. You take any plane like this, that
Yeah.
goes from any point on Z and go to cut X and Y. Then you have a mite.
Yeah, we actually reviewed that earlier tonight, Manu, on
Yeah.
figure 13.7. There's your X and Y and Z, and there's the mite right there.
Yes.
Ah,
So that's showing in the XYZ coordinates.
So
Wonderful.
Lee it is this thing here. You see, if I take this, look at it. This is XYZ, yeah?
yeah.
If I do this, if I do this, what you see inside is a mite. Yes.
Oh, I see.
You see
Cool.
that? Okay.
Cool. So Joe, how are you feeling? Welcome to our party tonight.
I'm feeling good. Feeling, I was attended a nice gathering this evening, and Fred, my thoughts have been with you the past couple days. So very much so.
Thank you.
And so so I'm doing pretty well. It's good to see everybody. And I appreciate Manu sharing his model with us and previously sharing it with me. So I'm excited about it. So it's good to be here. You look good, Steve. As do you. You always look good.
I came
That's
as
the real Steve, yeah?
I
The
came
real
as
Steve.
hippie tonight. I had
Yeah.
Fred send me all the hair he shaved off, and I've tried to like put it in and make sure that I'm.
Well, could you send some my way?
Yeah, no kidding. We'll have to have Fred do that because he's the guy who shares. He's cool. Yeah, I came tonight like a rock and roll hippie, so there you go.
There you go.
All right, any other comments or questions about what Manu said and what we're reading, and if not, we'll continue. And I think you were reading, Fred.
Yes. So we're on top of page 226, just after the synergetics
Right.
quote.
I think we have this last paragraph. Did you
Yeah.
read the partnership word?
Perhaps the most intriguing aspect of the coupler is its similar role in the cube and in the rhombic dodecahedron, thereby linking or coupling the two space feeders in a new partnership.
Yeah, that refers back to this.
Yes.
There's the two cubes, and here are the two dodecahedra with the octahedron joining them at the square surface
Yes.
of the
I
dodecahedron.
would like to point out something that
Okay.
that helped me, which we identified a long time ago. We identified that the triangle is the stiffener and the cube was the floor. The square was the floor. The triangle is the one that holds everything like in a shape that is fixed. So the triangle will always be the constituent of a matrix. And the square was the guy that allowed movement within the finite space. And
Right on.
we've seen that from all time. And then we've seen this thing here. What are we doing here? And what we've been doing for the past few weeks is to see space from the micro side. We have seen space a long time from the inflated, from the macro. That is, we are outside of a sphere, and then we could see the whole structure, the faces and the vertices. Therefore, have Euler's identity. We are looking at the outside of our world. That's why we use, because Euler identity talks about the border, the outside of it, the polyhedra. So every kind of rectangular, square, rhombus and triangle surface that closes is a polyhedra.
Right
Because
on.
you will have edges, it will have vertices, and then it will have edge and faces. That's what we've seen.
Right
But
on.
currently, from the few pages that we have, we realize that actually we're not out there. Let's see if we can fill that space. We're inside. These are material. Can we pack those things inside with us in order to fill it completely?
Mm.
And that's the view from the micro. And the objective of Becky here, was that viewing from the macro and viewing from the micro, the two will lead to the same result. That is, there is indeed some kind of, universal geometry, and that no matter where the observer is, that holds. Universe is, he calls it the eternally regenerative universe. So there is always universe in flow. Whether you are in it or you're looking for it from outside, it is there. And it's very important. And it goes from this thing here. All was built from this duality here of a triangle attached to a sphere, to a rectangle, to a triangle attached to a square. That's everything that allows it to flow. Sorry, I'm in the flow. My habit, yeah. It's for Lee here. It always comes from this guy here. This was our basic thing. You see this? It came from here. This guy doesn't move. This guy does it. Yeah. He does this. And he does this, and they're linked together in all forms to make structures that fill the space. And that is the eternal quest of mathematics. One set of mathematics is to say what are the set and the subset that describe everything that we need. That's it.
We've got to be very careful not to mix 3Ds and 2Ds. Triangle, everything, every shape in 2D can be triangulated. As we saw last week, not every shape in 3Ds can be triangulated, knowing that in 3D,
Yes. Yeah.
triangle is a tetrahedron. So there's a generalization that we cannot go, we cannot jump the space there. And it's very easy to do that jump, which should not be done. When we talk about plane intersections, when we talk, my shape is composed of faces that are all made of triangles in 2D. And then suddenly we went from a reasoning in 2D with triangles to a 3D because it's an assembly of faces that are triangles. It's a we've got to be very careful and have a little bit of rigor in our vocabulary when we describe this. That's what I
Yeah,
want
no,
to
I agree with you. I agree with you 100%, 125%. This was just to illustrate how we
Yeah,
can proceed. Yes.
I know.
Yes.
It's not to make you wrong. It's just to add
Yes.
a note of
Yes.
caution there.
Yes.
Okay, so
Because
we go. Yes,
if we look just 1 minute, if we
sure.
look at the problem of the phi, and we say the phi was different from the transcendental because it was a solution to
An
uh,
algebraic equation.
yes, a polynomial equation.
Yes.
It is basically because of this. And
Algebraic,
then
maybe
you run
maybe
into
not
things.
polynomial.
What is not solution to it is that we cannot tessellate it. Tessellation is a technique. Tessellation is a technique. That is, we try in building whatever we do, we take piece by piece, we put together. And then we see if we make form and we continue until we reach at something. But if I want to reach the horizon that is behind Fred there, that horizon that is curved like this, part of it, the part of a blue that is inside, maybe I could do it. And that is the phi. Then I have to find ratios. I call it a golden ratio that allow me to about describe that. But that one that is shining outside of there, that is going into the stars outside of it, I can't. Notice that on Fred's diagram, below it, I have the continent, and above it, I have the stars, and I have the horizon. It just, again, is nothing scientific. It was just an artistic observation. Okay, I'm through. Sorry.
Cool.
Okay. Shall
Any
I
other
keep going
comments?
reading?
What's that?
Anybody else got something? And then I keep reading.
Okay, good. I'm going to share the screen so that you can do that.
I have the book there. So
Okay, well,
that's so everybody can follow.
we're ready.
I'll wait for the screen to adjust.
Thank you. Should have it now.
Yeah, I have it. Volume and energy. The inventory of 24 modules, 16A and 8B, indicate that the coupler has the same volume as a regular tetrahedron with its 24 A-quanta. Both have a tetrahedral volume of 1. Recall also that a coupler consists of two 1/6 cube pyramids back-to-back, or 1/3 of a cube. In that chapter 10, the volume of the tetrahedron was shown to be 1/3 of that cube. Dissimilar in symmetry and shape, they are related by the shared unit volume, inviting comparison. The coupler is a different sort of minimum system, a semi-symmetrical space filler, in contrast with the tetrahedron's origins as the minimum systems of any kind, i.e. the first case of insidedness and outsidedness. Finally, we have to comment on the coupler's internal flexibility. The number of different ways to arrange 8 mites is greatly increased by the unexpected mirror symmetry. Since positive and negative mites can switch places, we actually have a pool of 16 from which to choose for each of the 8 positions. A coupler might consist of 4 positive and 4 negative mites, or all positive mites, or all negatives, or any of the possible combinations in between 0, 8, 1, 7, 2, 6, 3, 5, etc. until 8 and 0. These are numbers is 0 positive, 8 negative, up to 8 positive, 0 negative. Then within each of these 9 possible groups, the mites can be switched around into 4 different arrangements. A few of these combinations are shown next page. The resulting 36 varieties of couplers all have the same outward shape, but in Fuller's view, their internal variations represent important distinctions in energy behavior. And I quote synergetics now. Hang on. When we discover the many rearrangements within the uniquely asymmetric coupler octahedra of volume, I will start again the citation. When we discover the many arrangements within the uniquely asymmetric coupler octahedra of volume 1, permitted by the unique self-intercalated orientability of the A and B modules without any manifest of external confrontations alterations. We find that under some arrangements, they are betting the x-axis interconnectings between nuclear spheres and their 12 closest packed spheres, or the x-axis interconnectings, etc. I think commas were in scarce supply in 80s.
You think what was in scarce supplies?
Commas, punctuation.
Oh, commas. Yeah, I gotcha.
That's a difficult sentence to read.
Well, Bucky never used commas, so that was something. Okay, good. Different
Can I comment?
rearrangements of eight mites in the
Is that
coupling.
clear? Should I reread that?
But can I comment before we
I
go
think it
into
is
that?
pretty clear,
Okay.
but does somebody want to hear it again, you guys? Go ahead, Manu.
I want to make a comment.
Yeah.
To me, there is some very important thing that is said that in the general arrangement, you can arrange the 8 in such a way that all are the same sign. That is 2 times. And once when half is of one sign and the other half is the other sign. What does it remind you of? All are half of is positive and half is negative is what Bucky called the universal constant. Is the gravity. The local gravity. All positive and all negative is 2 phases of dispersion and in. What is that? Left leaning, right leaning radiation. So the left brain radiating in and the right brain radiating out like that. So gravity, since all is in equilibrium, gravity is locally twice as intensive as radiation. Do you see that?
Well,
Just from the general orientation, say you can orient it 3 ways. One way is to have half positive and half negative. The result of that is gravity, we know. Is a universal constant. It does this. The other way is to alternatively, there are only 8. Either all the 8 are positive or all the 8 are negative. What is this, Steve? It is your radial torus that come like this. Wow. And come in, back in. The fountain that flows out and then it channels back in. When it flows out, all the 8 branches are positive. When it comes back in, all the 8 branches are negative. And that is the electromagnetic. I've always shared that the electrical are concentric loops of flow of energy that does this at the equator level. That is the electrical field. The magnetic field goes through a slice that is perpendicular, through a window that is circular. It goes like that and come out. Goes like that and come out. And both are the electromagnetic that we see, the double torus. This guy on a plane doing this in concentric, like ripples. When you drop a rock on the surface of a calm lake, you have horizontally perpendicular to the trajectory of the rock an expansion. You have stationary waves that seem to be expanding like that. that way. That is similar to what electrical does. And electricity is always defined in loops. And then the magnetic one is the one that is alternatively same sign and alternatively same sign, but opposite signs. So therefore, the whole of that describes the sphere is the electromagnetic field, the electromagnetic field. So you have to imagine the electrical as, imagine that this was the circle, the electrical is doing this. It's turning like that, but keeping the shape. So it's turning like that. So therefore, what you call an equatorial axis, and the magnetic is going through this thing, coming out and coming back in. When it comes out, it's all positive. When it comes back in, it's all negative. And all is, this guy is turning and that guy is doing that. So the resulting is the array of the electromagnetic field that we see. That slices everything in the universe into a component, is true everywhere, into a small component of it. And that component, in my opinion, is, I wouldn't say it, that is jumping too far, but it is that thing. So you see the matrix, that is forever, you know, all the animation that we have is an illustration of that basic duality. That's what I understood when Fred read the three shapes that can result in the combination of those 8.
Okay. Everybody complete at this point?
Shall I keep going?
Cool. All right, let's go back after it.
We just we start again under figure 3.9, page 227.
Yeah.
I'll wait until the
Should be up in a
moves.
flash here. Okay, there it should be.
You have it? Okay.
Yes.
Yes.
So again, quoted from Synergetics. When we consider that each of the 8 couplers which surround each nuclear coupler may consist of any of 36 different AAB intramural orientations, we comprehend that the number of potentially unique nucleus and nuclear shell interpatternings is adequate to account for all chemical elements' isotopal variations, as well as accommodation for all the nuclear substructurings, while doing so by omnirational quantation. Isotopal is one element, as in my table of the element, can have a different nuclear structure, like uranium-235 and uranium-238. That's isotopes. That's isotopal. So what it says there is that these different structures of couplers can account for every variations of the chemical elements in universe, and not only in their chemistry, but also in their nuclear structures. In other words, energy travels in one direction or other, depending on the arrangement of the A and Bs, which are oppositely biased. Synergetics thus accounts for nature's incredible variety and complexity, despite its small number of different constituents. The secondary level of organization involves grouping the different couplers. The secondary level of organization involves grouping the different couplers together and results in an explosion of potential variations. A modules and B modules can thus be rearranged into orderly octet configurations in myriad ways. Clusters might appear quite chaotic in some locations and precisely ordered into whole octahedra and tetrahedra in others, while the overall space filling matrix remains intact. As in genetics, the small number of simple constituents are able to generate a virtually unlimited repertoire of patterns.
Right on. Comments, questions? Well, that actually finishes that
Do you,
section.
do you really want comments? Because this is going to be highly.
I do have a comment.
Yes.
Good.
I do have a comment. Again, it's a comment about vocabulary, and this time it's not a critique of Bucky, it's a critique of Edmondson, the Amy Edmondson.
Yeah.
The vocabulary used here, as in genetics, a small number of simple constituents are able to generate a virtually unlimited repertoire of patterns. We have to be very careful. We live in a finite universe. And when she says myriads, which means thousands of, and virtually unlimited, it is misleading in my opinion, because this can be counted. It's a matter of enumerating these patterns and their associations, but this can be counted. So we are talking about enumerations here that may be large but are not infinite.
Can I counter that?
Yes, please.
Okay. The reality is this one, is that what we have described here to describe this whole world is 4 derivations. 4. We first did 2 derivations to arrive at the tetrahedra and the octahedra, the final stuff. And we've now we've now cut that octahedron twice. We saw it here. So when you do 4 derivation and you want to come back to set, that is patterns, because we always see in pattern recognition. There's no other way. We are blind. We have senses that countings, see forms, and then relate. That's our technique. We don't have any other technique apart from believing. So when we do that, remember that we are counting the C's. When you go from a derivation now and you do integration of a derivative, I can say the derivative of x squared is 2x. But I can say that by integrating 2x, I'm going to have x squared. I'm going to have a class that is virtually infinite, because I'm going to have x squared plus 1 plus 2 plus 3 plus whatever is a real number. And that is the magic of finiteness. And depending on the technique that we use from inside, we cannot solve a problem in a definite way. And that's what accounts for me philosophically about the eternally of universe. Because it is forever dividing. It is the business of dividing. Until some transcendental, let me call it force, say, hey, stop, that is finished. Your time is gone. This is the end. But we cannot do it from inside. From inside, we can only divide what is given to us. That's my position. That's why I was warning that it is philosophical. It's not scientific. It's not a demonstration.
Yeah, I understand. I understand,
Yeah.
and surprisingly, I agree with you.
Okay. Okay.
Emphasis on surprisingly. I think
Right.
we're not in disagreement here. The reason is that we're looking at the same thing from 2 different angles. You're looking at it from derivate it and then reintegrate it. I'm looking at it from dividing it and then reaggregating it. And that's slightly different. From a finite number of variations, you can always count what the output is. But what you're saying is that, and if we put it on plane of integration, then there's always uncertainty as to its final position in space, I would say, to take
Yeah.
to take vocabulary that is easy to understand. Okay, thanks. That was interesting. Shall we do the
Oh, cool.
review of all space feeders?
Yes,
Uh,
I think we should do.
Well, I guess we can. Let me start that baby up.
Sure.
It's 12:30. We've got 2 pages to go. We may have a chance to finish the chapter.
Yeah,
We can do,
wonderful.
we can do because at the level where we are now, we've passed the level of reading line to line. Our discussions are constantly looping and feeding and feedback. We're having feedback and we're enlarging. And sometimes we're anticipating where she is in her organized book.
Okay.
So I think that, yeah, we can read to the end because what we have to express, we have probably expressed it in comment during the time of reading.
Okay.
Cool.
Okay. I'm still going to read line by line.
Good.
Mhm.
Okay, review of all space feeders. Dismantling the cube, we saw that each of its 6 inverted pyramids breaks down into 4 mites. What does this tell us about A modules and B modules? 24 mites yield a total of 72 modules, with twice as many A's and B's, or 48 to 24 ratio. This 2-to-1 ratio gets to the modular heart of the octahedron tetrahedron prerequisite for space filling, as developed in the last chapter. Neither tetrahedra with only A's nor octahedra with equal numbers of A and B's can qualify as space filler. So far, so good. Thinking only in terms of A modules and B modules, what proportion of tetrahedra and octahedra would we need to satisfy the recipe of 2 A's for every B? The octahedron's 48 B's must co-occur with 96 A's. The octahedron itself supplies half of them, but 48 A modules are still missing. 2 tetrahedra will provide exactly the right number of A modules to complete the formula, thus reconfirming the 2-to-1 octahedron-tetrahedron ratio discovered in the previous chapter. The 48 mites in the rhombic dodecahedron are easily dissected into 96 A's and 48 B's, or a total of 144 modules, with twice as many A's as B's. Bucky-Fuller's spheric does not contradict the growing evidence of a general rule. A modules and B modules in the truncated octahedron, also space filler, can be counted by recalling the numbers of internal single-frequency tetrahedra and octahedra determined in the last chapter. 32 tetrahedra with 24 A modules each contribute 768 A's, while 16 octahedra consist of 760 A's and 768 B's, for a total of 1,536 A's and B's, for a total of 1,536 A's and half of B's. We can begin to have confidence in the reliability of our 2-to-1 ratio, especially in view of the jump to much larger numbers. With a total of 2,304 modules, this is the smallest truncated octahedron outlined by the IVM vertices, isotropic vector matrix vertices. Fuller's inventory of all space feeders lists the truncated octahedron with twice the linear dimensions and 8 times the volume, consisting of 18,432 quanta modules, rather than the smaller version. The reason for this choice is not clear. However, the magnitude of these quantities hints at the complexity of his modular system, in terms of both the variety of systems that can be made from the modules and the number of rearrangements within those systems. From these numbers, it is evident that although the quanta module helps us understanding the conceptual essence of many polyhedral intertransformabilities, they are very impractical for hands-on experimentations. So many modules are needed to make complete polyhedra that this system does not offer an ideal strategy for model making. Instead, we might utilize the analysis to work out relationships on paper. From the above examples, we can see that the A modules and the B modules get to the root of the two tetrahedron, one octahedron rule developed in the previous chapter. Because the earlier analysis depended on disassembling its two basic units, it was necessary to probe further to isolate the real quanta. A modules and B modules, which cannot be symmetrically subdivided, were isolated as the true quanta, with which to measure and analyze related polyhedra systems. Impressed by the geometric significance of these modules, Fuller proposes that somewhere within this discovery lies secrets with far greater application than just to geometry. And here I cite synergetics. The A and B quanta modules may possibly quantize our total experience. It is a phenomenal matter to discover asymmetrical polyhedral units of geometry that are reorientably compositable to occupy one asymmetrical polyhedral space. It is equally unique that, despite disparate asymmetric polyhedral form, both have the same volume. The unit volume and quanta energy The unit module and energy quanta values provide a geometry elucidating both fundamental structuring and fundamental and complex intertransformings, both gravitational and radiational. From the energy associations to their remarkable symmetry, these modules synthesize much of Fuller's research. Significant relationships to physical phenomena may well reward continued investigation, for nature also deals with discrete quanta, creating endless variation through synergetic recombination. Fuller reasoned that his geometric quanta, the end result of a systematic and logical progression of steps, must relate to physical phenomena. The approach is typically Fuller's. Assume significance until proven otherwise. In essence, he suggests that tiny whole or discrete systems should replace irrational unending digits, somehow providing a comprehensive rational coordinate system.
Congratulations.
These are big words.
We finished reading all those words.
Yes.
Any comments or questions?
And I was not interrupted by any comments. That tells me that everybody wants out of this chapter.
That's right.
No, I want in. I want in. I want in because it provides us the key. I've always insisted on the four quanta. And then that the fundamentally, and then together with the duality principle, that is a 2-to-1 ratio. That is, which has the base, account for everything that is rational. Rational being intertransformable. Rational. The second thing is, I think that with the computing power that we are having today, we're going to solve these problems. Because when Amy says it is impractical, because when she writes this, there's no, we haven't talked about the quantum computing here. When these things start crunching their numbers, I'm sure from the CERN, we're going to hear something. Or from somewhere in Russia or in China or in the US, we're going to hear something that is fundamental in the direction of asserting this. That's my conviction. You might say it, my optimism.
I think every computer scientist would be very happy to get rid of rational numbers. and irrational numbers. Everything integers, and everybody's happy.
But what if all what they crunch and the result that they arrive at are describing something that is rational within the boundary? Because that's Becky's painting. Becky says, and that is given, is that within universe, everything is rationalizable. Either it is rationalized by natural form, the polyhedra, that can be accounted for into octahedra and tetrahedra, or it is accounted at the border. Just I like that picture behind you. It's accounted at the border through stellation and an infinite series that converge towards something finite in a certain ratio that we call the golden ratio. So according to him, we can account for everything inside the universe that continuously intertransform by that model. That's what he said.
I feel very unsafe when we go to the limits of mathematics.
But that's what he said. That is his hypothesis. Let's put it that way.
So there's a big discussion in mathematics. Actually, it's a bit obsolete now, but there's a big discussion. There was a big discussion between the tenets of continuity and the tenets of quantization in number theory, but in geometry also.
But listen to this. Listen.
I don't like this discussion. I feel unsafe when I look at that because that makes you realize there's no foundation.
Yeah.
Okay, but listen to this that I say. That is my belief.
Oh, okay.
I'm saying this is not scientific. It is in the realm of belief. I'm saying the boundary is not hermetically closed. The boundary is always there is something. It has it's like a post. Imagine you have a camp, you have a post, and that post reflects some stuff out that rejects some of the applicant to come in and admit some. So for as long as they can admit while keeping the order inside, we have a rational inside. But there will come a day that the boundary itself will be abolished because he has reached. That's why I say my belief. I see your face already. He has reached the limit of its utilitarian role by whoever created the system.
Okay.
And that's the end of that's the end of that universe.
Okay. So
there's a quote from somebody, I forgot who said that, who said, before you tear down a fence, and a fence is a symbol for boundary, you should have a clear idea of why the fence was put up in the first place.
Right.
Exactly.
Yeah.
Well, I really like that because that hits my whole dilemma on the head. Whoop. Lee, you just jumped out. How come?
Not me.
Well,
My phone.
come back in. Did it lose its power?
No.
Okay, well, come back in. She can listen to what's going on, but it's nice to see her mug over here on the screen. So I have a couple of problems brewing. It could be our takeaways. You know, we only have 15 minutes left. Maybe it's time for takeaways, and I'll put my stuff in there. So, Richard, you've been kind of quiet tonight. How are you feeling, and what do you got for takeaways tonight?
I think the main takeaway was to see the visualization of the half an octahedron, the square-based pyramid, with that one connection and the flexible square underneath. to turn into two end-to-end tetrahedrons. So I appreciate that, and I have my own modeling here, so I was able to follow along and and construct what Manu was constructing and demonstrating. So that's my big takeaway. My takeaway from the last sort of half hour or so is because of the real life situation of trying to deal with a gimpy knee that doesn't seem to want to be rested and feel better. So I think in the spirit of tensegrity, we may have a tensional sort of factor within the knee joint having given way for some reason. It just happened spontaneously. So again, I'm taking away in real life an apparent sort of tensegral uh, separation or breakdown. And boy, does it ever immobilize you in a hurry. Um, so that's my takeaway, and I appreciate your patience in allowing me to step aside for the time that I did. Um, Joe, how are you feeling? What's your takeaway?
I'm feeling, pretty good. It it was, that was a lot, and I was fortunate enough to go over a lot of it with Manu on earlier this week. But fundamentally, what I think that the ultimate difference is it it highlights the importance of thinking about things and how they relate to one another. And that's what Manu was able to demonstrate there a moment ago. As he was walking us through it, and even as he did the other night, Wednesday, there's a deep understanding of how the nodes actually interact with one another. And that deep understanding is understanding, the relationships themselves. And so in thinking in terms of relationships, uh, you know, I have a feeling like in certain cases that we're looking for things that are, I don't know, binary in certain ways. I guess instead of looking at things in terms of relationship, and it, it I I heard the term like kind of like thinking crookedly, meaning that our perception of reality is not necessarily, if it's not aligned properly, that it has a way of actually impacting, our behavior, um, and how we view the world. And if we don't view it through relationships, then obviously that's problematic. And I'm thinking about it in terms of mostly what I'm thinking is like Albert Ellis's RABT approach, and he talked about things like crooked thinking and the inability to perceive reality properly. And I mean, what Manu's showing us is that, by showing us all these connections, um, that how to, and essentially showing us a new geometric model, and not necessarily thinking in terms of um, boxes versus thinking in terms of connections, then, or the Cartesian system, so to speak, then that changes your perception on how you look at the world in general. So that's my takeaway, is to kind of see how it's the distinction between looking at the connection between things and but aside from looking at things in boxes and in very stark categories, I would say. So, in any case, Lee, how are you feeling? What would you like to take, or what did you take away from today?
Well, I think I am now beginning to understand what a mite is. And then you guys put in all these long words that I have no idea what the meanings are. I have to sit down with a dictionary and go through the book while I have it available to understand it. Maybe have Steve go through a dissertation with me. I did have a question, but I have lost the word in the book. So it's in the last paragraph in the book. And I didn't understand that at all. It's a simple one, an octa. Is that what it's called? An octa?
We can bring up that last.
I can reread the last paragraph if you want to stop me when I'm done.
Please.
Okay. From their energy associations to their remarkable symmetry, these modules synthesize much of Fuller's research. Significant relationships to physical phenomena may well reward continued investigation, for nature also deals with discrete quanta, creating endless variations through
Quanta.
synergistic recombinations. Yes?
The quanta. You've mentioned two different kinds of quantas. So what is a quanta in math?
A quanta is a unit that cannot be subdivided.
What? What was that?
It's a unit of whatever that cannot be subdivided. You can no more divide it.
It's a quantity or a unit. It's a thing.
You muted, Steve.
Any smaller?
Yeah.
Aha. I knew that quantas were a division, but I didn't know that it could end. I thought it would be infinity.
It's actually a quantum.
Basically,
Quantum.
the essence of quanta is that it can no more be divided. It's like quantum physics is based on quanta, which is based on granules instead of infinitely small particles.
Mm-hmm.
There's a limit to which you can go. Steve, you're still muted. There's a limit to which you can go in.
I just
I
repeated
thought
what you
it
said.
might get to infinity.
Nope, there's a bottom. There's a bottom and it's not infinite, and there's a top and it's not infinite. Bucky describes the universe as a finite entity.
That's right.
Yeah.
Okay, thank you.
There may be infinite possibilities within the finite reality, but reality is finite.
There has to be a boundary.
Yeah. So
Was
are you
there
complete
something
then,
else,
Lee?
Steve?
I am. Fred, what have you, how do you feel, and what have you taken from this evening?
Thank you, Lee. I'm feeling complete with this chapter. In other words, I'm done. That's that's how I feel about this chapter. I probably will go back to it later, but I think we've beaten that horse of that quanta horse until it's dead and re-dead. That's how I feel about that. And my takeaway is that reading aloud helps with comprehension. That's my takeaway. So I may start reading aloud even without
Meet your new Dell
Sorry.
PC with Intel.
Without being on my own, without reading for somebody, reading aloud for myself. So that's my takeaway. And Steve, I think you're the last one. Yes, Steve, thank you. And how you
Manu,
feel and what is your takeaway?
Manu has to go.
Oh, Manu has to go. Sorry, Manu. Manu, how you feel and what is your takeaway?
I share your completeness. I'm happy. And then what I'm taking away is a prayer that says this: Lord, help me to use what I understand to help make this world a better place for most of us and to understand the things I cannot change. That is my prayer.
Good.
So, Steve,
Yeah.
how do you feel? What do you take away?
Good. Amen to your prayer. That's cool. I'm into quanta because, Planck came up with his quantum. And Donald Hoffman definitely says there's a quantum, and underneath this thing, there's an amplituhedron, is what Donald Hoffman says. But I think he's just afraid to get on the Bucky train. So we'll see about that. I have some basic underlying things that are driving me crazy about this whole thing. Um, you know, the whole idea about quantization, you know, quantum mechanics has been trying to quantize gravity, figure out what gravity is, and haven't been able to do it. And of course, that's why most people say that quantum mechanics is bankrupt. It's gone as far as it can go, and we need to do something else. And so I think we're getting into geometric symmetry as an underlying structure for material reality. I actually think that. I'm still confused about space filling. I think space filling must be about energy because I'm wondering, I get all these geometric fluctuations that are occurring in the isotropic vector matrix, but how do atoms and electrons and quarks fit into all that? I'd like to see that happen one day. Maybe that's the great unifying theory. You know, first unify relativity and quantum mechanics, and then figure out how to unify Bucky and all that. I don't know. So I'm space filling is interesting. I can see spheres, I can see energy, I get that, but it is still confusing to me about space filling. And I think Manu is going to be particularly excited because the next chapter, Manu, it's all about great circles. And you've tried to bring in great circles 3 or 4 times into this conversation. So we're heading into the realm of great circles, my friend. That'll what we'll be reading next time. Also, I took your photos that Joe put in the chat. I put them on my hard drive and I kept track of their numbers, figuring that the lowest number is probably the first photo. So I organized them. I'm going to create a PDF file and I'm going to put them in and attach them to our thing. So all of your constructions will be in a PDF file for a future review. You went to a lot of work on that, and that was really cool. I enjoyed seeing little notations, and I hope your wife doesn't get too mad at you. Also, DNA only has 4 letters, and I don't know if there's a finite way to claim about how DNA manifests. Those 4 letters uh, kind of resolve into create words or up to 64 codons. Those codons, some of them refer to amino acids, some of them are amino acid stoppers, and there are 3 billion letters in in an average human being. So 4 units to create a pretty much huge stack of non-repeating instances. It amazes me. And if we get back to Stephen Wolfram, we go through his Rule 30. I think he's excited about his Rule 32, where he just turns his little automata on and off. And with very simple beginning rules, the world is crazy. It looks like chaos. So, to those who don't have the discerning eye. So, anyway, those are a few of my musings and takeaways. And one day I'll really get what space filling is all about. Yeah.
Can I say something
Sure. Go ahead.
for you? Space filling, Steve, is that is space filling of energy. You're always
Yes.
forgetting this guy. Look at this guy.
Yeah.
You see, look at the way I hold it.
Yeah. Beautiful.
It's turning. But look at this guy. This guy exists.
Yeah.
Remember, in what we see, that is 75% of the tetrahedron. We did not talk about it. It doesn't mean that it's empty. That is the hidden energy. That is synergy. That's what is in to be in reserve, to be deployed when necessary. What I mean is that, look at this one. The first one has a name. We color it. The second one has a name. We color it. The third one has a name. We color it. It's part of these two. But this guy has no name. And this guy is turning and is rocking. Is rolling and is rocking.
I'm into rock and roll.
Rolling and turning. That's it, what he does. It's rocking, it is rolling, and that is turning. And that's what we keep on seeing. Remember that you are, the observer are you, in relationship to me here. You don't see all that all the time, but it is filled. This space is filled.
Cool.
And I'm God here. I'm playing God. So to those who don't believe, this got to exist. This guy also has, he ought to hold this thing visible and that one negative there for this guy to do this, for it to do this.
We're gonna start a pilgrimage to your door, Manu, so that you can explain the universe to everyone.
I think God wished he was Manu.
Yeah.
I believe. I'm a believer. So
I love it.
I believe.
Thank you for your link about AlphaFold 3, Joe. And I'll review that. Okay, you guys.
Worth looking into. I mean, Demis Hassabis is an interesting guy.
Cool. I won't be here next week, probably. I'll be in San Diego on a boat out in the ocean with my brother. He has a
your brother, yes.
He has a sailboat, and I'll be out there on his 30-foot sailboat sailing. We're going to latch up in Catalina or someplace. So I won't be here Saturday night. So maybe we can do Fred again. And Fred, you can store them up and send me the links. I still haven't processed all that information you sent me. I'm trying to catch up. But
let me give you an appetizer, Steve. Go to page 260 just for us. 260?
Yeah, I told you great circles were coming.
No, but something more interesting.
What could be more interesting than Great Circle?
Nothing is more interesting than Great Circle.
Absolutely right. Yeah, I've got, page 260.
Yes.
I've got page 262 crimped and it's in the way.
Yeah. See, look at figure 15.1.
Yeah.
That's the whole stuff.
Yeah, that looks like the mincemeat tarts that my grandmother used
to make. It's a soccer.
Okay,
it's a soccer. It is a soccer. Is what we play. The most popular sport in the world is soccer. That is a soccer ball. That is exactly what the soccer ball is.
Yeah, 6 interwoven great circles. See, I knew you'd be excited about a reading. Okay.
So next week I'll send an email with the link for next week if you will.
Okay.
That'll be good because I might be a little.
Yeah.
So do you mean that is Fred that is going to send the link?
Right.
Yes.
Yeah.
Okay, good.
Yes, I will send the link and with an invitation and I'll do the recording like we did when Steve was
good. I've got the recordings downloaded. I haven't yet processed them into the archive yet. So thank you for the extra time. All right, everybody.
Sure. All right,
I'll see you 2 weeks from
right.
tonight, and then I will see you on Wednesdays without any problem.
Good
All
night.
right. Thank you. Bye-bye.
Bye-bye.
Bye.
Bye-bye.